Well, hi there, boys and girls. Today we're going to talk about special right triangles, which hopefully is a review from geometry. And we're going to talk about two in particular. Well, really the only two special right triangles I know, and that's the isosceles 45, 45, 90, and then the 30, 60, 90. We are going to need these, and we're going to use them all year, and you'll also use them in calculus. And they all come down to two different ratios. And so we're going to do the 45, 45, 90 first. And so we're going to take a look at this. If YZ has a length of 1, then fill in the lengths of the other two sides. So YZ is over here and it has a length of 1. And I'm going to see that it's across from this 45-degree angle. Since this angle Y is 90, that only leaves one possibility for angle Z, and that's also 45 degrees. And we've made an isosceles triangle. If you have two angles that are equal in a right triangle, then the other sides have to be equal to each other. So that means that XY has to also be 1. So this is isosceles. They're both across from 45-degree angles. Therefore, they have to be equal to each other. You can use the Pythagorean theorem, or you can remember from geometry that once you do a squared plus b squared equals c squared, you will get that the hypotenuse, and remember that's that fancy long word for the side that's across from the 90-degree angle, works out to be square root of 2. And so that's the ratio of those three sides. 1, 1, square root of 2. So let's take a look at part B. If YZ had a length of 5, then what would the lengths of YX and XZ be? So let's take a look at this. Turn it around over here. Try and make that more of a right angle if I can. Yeah, that looks pretty good. Okay, so I'm going to put an X here and a Y there and a Z here, and we've got the right angle here. We've got if YZ had a length of 5. Well, here's YZ is 5, and we still have angle X be 45 degrees, or is 45 degrees, and angle Z is also 45 degrees. Fairly simple, it's isosceles, so XY, or YX, has to be 5, and XZ would be 5 square roots of 2. That comes directly from the Pythagorean theorem, or your 1, 1, 1 square roots of 2 ratio. This one is 5, 5, 5 square roots of 2, or it could be 20, 20, 20 square roots of 2. It's a pretty easy ratio in a 45, 45, 90. Now let's take a look at one that might be a little more complicated, and we're going to set up a proportion to solve that one. I just whistled, sorry, when I said that. Alright, that looks sort of right there. And I'll put an X here, and a Y here, and a Z here. Got our right angle and our 45, 45. Alright, now we have that XZ has a length of 3. And this is a little different because if this had a 3 square roots of 2, it would be easy. I would just put a 3 on YZ and a 3 on XY. But this does not have a square root of 2 on it. So it might help you to set up a little table. And I lost my line that separates. There we go. So we're going to set up a little table here. The ratio in a 45, 45, 90, these side lengths are across from those angles, are 1, 1 square roots of 2. What we have, however, what we have is across from the 90-degree angle, we have a 3. And we want to know what goes here and what goes here. And so what you can do is you can set up a proportion. We can say that we thought we were going to have a square root of 2, and it really turned out to be 3. We want to know what happens if the 45-degree side is a 1. What should our 45-degree side be? And so we can cross multiply to find this. So x square roots of 2 is equal to 3. So x equals 3 divided by the square root of 2. And I'm going to write that here. And there might be some of you that remember from Algebra 2 or Geometry that there's a way of rationalizing the denominator. And that's true, but that is not necessary, and I will rarely rationalize my denominator. The reason for doing that disappeared with calculators. So it's just like with Boy Scouts, they don't start fires with sticks and stones. We really don't need to rationalize our denominators anymore. But for those of you that still feel the beat down from your Algebra 2 teacher, I'll go ahead and show you the rationalized form. 3 divided by the square root of 2, you multiply the top and bottom by the square root of 2, and we get 3 square roots of 2 over 2. I don't know why that looks simpler to some of you, whatever, but that is equal to 3 over the square root of 2. If you don't believe those are equal, type them in on a calculator and you will see that they are. That means that this other side also must be 3 divided by the square root of 2. Let's go take a look at 30, 60, 90. 30, 60, 90 has a different ratio. There's different angles, and so I'm going to put a 30 degree here, and that ratio will be a 1 across from the 30, a square root of 3 across from the 60, and then a 2 on the hypotenuse. So it says if SR has a length of 1, fill in the lengths of the other two sides. Well, I just did that. The side across from the 60 degrees is square root of 3, and the side across from the 90 is a 2. Alright, so let's answer this next question. Try and pull this out here. This is not going to look exactly like that one, I apologize, but we're going to say this is not drawn to scale. So there's our 60 degree angle, there's our 90 degree angle and 30 degree angle, R, S, T. If SR had a length of 7, SR had a length of 7, what would the other two lengths be? Well, it's the same ratio. The quickest way to do this, at least not the quickest, but the way I do this is if I know the side opposite the 30 degree angle, I double it to get the hypotenuse. See how this ratio is a 2 to 1 ratio in our base 30, 60, 90? Since we know that the side across from the 30 is a 7, then I'm going to double that to get the hypotenuse. And then the side across from the 60 degree angle, I'm just going to tack on a square root of 3 to the side that has across from the 30 degree angle. So we multiply that times the square root of 3, and that would be that answer. So let's do one last problem here where it's not so easy, and proportion might help you. And we'll draw our triangle again. Again, not perfectly drawn to scale. So we've got an R, an S, and a T. Here's our right angle, here's our 60 degree angle, and our 30 degree angle here. Now it says, what about ST? What if it has a length of 5? And you can see how this is a tad different because earlier our sides across from the 60 degree angle had square roots of 3 tacked onto them, but this one does not. So I'm going to use a ratio to solve this. The side across from the 60 used to have a square root of 3 on it, but mine really has a 5. And we want to find out what about the side across from the 30 and what about the side across from the 90 degree angle. So let's do that proportion here. So I'll do the square root of 3 over 5 is equal to, let's find the hypotenuse first, is equal to 2 over x. And then we're going to cross multiply, so x square root of 3 is equal to 10. Divide both sides by the square root of 3, and we're going to get that x, the side across from the 90, is 10 divided by the square root of 3. So this is 10 divided by the square root of 3. This also happens to equal, for those of you that love rationalizing your denominators, 10 square roots of 3 over 3. I believe that's the last time you're going to see me do that. But just to show you that it's equal, there it is. Now the side across from the 30 is always half of the hypotenuse. Remember that 2 to 1 ratio? Well, do you know what half of 10 over radical 3 is? It's 5 over radical 3. So I believe that's enough, and tomorrow in class you guys will be practicing 30, 60, 90s, and I will see you then.